Early on, scaling up power meant scaling out. To manage three-phase systems, engineers simply wired three separate single-phase transformers together. Today, that approach is largely replaced. At a modern substation, you'll see a single, massive core-type transformer handling the entire three-phase load. Consolidating 3 units into one reduces the required floor space, cuts the total weight, and lowers manufacturing costs by about 15%. But packing 3 phases into a single casing requires precise alignment. The internal mechanics rely entirely on exact phase geometry. Inside the iron, engineers must choose between 2 foundational wiring topologies, the star, also known as Y, and the delta connection. These specific internal configurations dictate how phase vectors and voltages are manipulated, setting the mathematical limits for the entire system. Look at this diagram of a transformer core. You can see the primary and secondary windings wrapped around the iron, with the main magnetic flux traveling in closed loops. In a 3-phase system, you have 3 distinct alternating magnetic fluxes simultaneously traveling through that framework. Because the 3 phases are offset by exactly 120 degrees, the sum of their magnetic fluxes at any given instant is mathematically 0. This zero-sum cancellation makes a central return leg for the flux unnecessary in the core's physical construction, as the magnetic fields balance each other out perfectly. This diagram shows the Y, or star connection, located at the top. Notice its radial geometry, where all 3 phases meet at a central neutral point. The Y configuration is highly economical for high-voltage systems. Because the voltage across any single phase is only 1 over the square root of 3 of the total line voltage, the amount of physical insulation required is drastically reduced. Now look at the lower schematic. This is the delta connection. It forms a closed loop, completely eliminating that central neutral wire. Delta excels at harmonic trapping. The closed delta mesh provides a continuous circulation path for third harmonic currents, keeping them out of the transmission lines and ensuring a clean sinusoidal output. Engineers deploy Y to save money on insulation in high-voltage scenarios, and they deploy delta to maintain harmonic stability in high-current applications. Electricity rarely stays at a single voltage. Substations must constantly bridge high-voltage transmission lines with the lower-voltage distribution grids that power homes and businesses. This schematic details the internal windings of a YY transformer, establishing perfect baseline symmetry. To step voltages down at the end of a transmission line, engineers alter the symmetry, crossing the topologies to pair a primary Y connection with a secondary delta connection. Conversely, at generating stations, they use a delta Y setup to step the voltage up. This has the added benefit of providing a grounded neutral on the secondary side for distribution. Crossing these configurations alters the math. The ratio between the secondary and primary line voltages incorporates that same 1 over the square root of 3 factor, modifying the inherent transformation ratio of the coils. But crossing topologies introduces a strict geometric consequence. By linking a radial Y to a closed delta, you force an absolute 30-degree phase shift between the primary and secondary line voltages. Crossing configurations is the most efficient way to manage massive voltage jumps, but it permanently alters the temporal phase alignment of that entire grid segment. If one transformer in a closed delta-delta bank burns out and fails, the symmetry is broken. To maintain 3-phase service, engineers can run the remaining 2 units in an open delta, or VV architecture. You might assume that keeping 2 out of 3 transformers means your capacity drops to roughly 66%. The math dictates otherwise. An open delta bank actually operates at exactly 57.7% of the original closed delta rating. Power engineers measure this inefficiency using the utility factor, which compares the actual operating capacity to the available physical capacity of the hardware. The open delta has a utility factor of 0.866. That means even the 2 functioning transformers are not being fully utilized. Look at the lower phasor diagram here. Notice the asymmetrical angles of the current vectors. In an open delta setup supplying a balance load, one transformer operates at a power factor of cosine 30 minus phi, while the other runs at cosine 30 plus phi. This proves that 3-phase power does not physically require 3 coils. It relies on relative vector geometry, allowing the system to keep running in an emergency, but at a severe mechanical efficiency cost. When true 3-phase power needs to be converted into an isolated 2-phase system, we use Charles F. Scott's TT connection. The setup requires 2 transformers. The horizontal main transformer is built with a precise center tap on its primary and secondary windings. The vertical teaser transformer connects directly to that center tap. To ensure balanced phase voltages, the teaser's windings must be designed to handle exactly 86.6% of the line voltage. Unlike the open delta emergency fallback, the Scott T is intentionally designed for high efficiency. When both transformers are operating at their designed voltage ratings, the Scott T achieves a combined utility factor of 0.928. The Scott T provides the superior geometric solution for phase dimensional shifting, extracting significantly more usable capacity from the hardware than a VV configuration ever could. As grid loads increase, a single transformer often isn't enough. Utilities must link multiple transformer banks in parallel to safely scale up capacity. Parallel operation requires strict uniformity. The transformers must have matching voltage ratios and identical per-unit impedances to ensure they share the load equally. But the absolute boundary condition is geometric. They must have zero relative phase displacement. This is why it is mathematically impossible to wire a Y-delta bank in parallel with a delta-delta bank. Even if their voltages match perfectly, that inherent 30-degree phase shift puts the waveforms permanently out of alignment. Ignoring this displacement causes a massive voltage difference. The result is an instantaneous catastrophic short-circuit current that will absolutely destroy the hardware. Phase geometry acts as an absolute physical boundary for grid expansion. Mathematical misalignment cannot be bypassed simply by installing more copper and iron. When you look at the towering high-voltage lines stretching across the landscape, you are actually looking at a physical expression of vector geometry. We rely on the symmetrical star connections to save on insulation costs, and we deploy closed delta configurations to trap harmonics and stabilize the current. To transfer power across varying voltage levels, we cross those topologies with Y-delta transformers, deliberately accepting the permanent 30-degree phase shifts they inject into the grid. And when symmetry breaks or dimensions need to shift, we lean on the asymmetrical open delta and Scott-T architectures, trading physical hardware efficiency for operational continuity. Every single connection, whether scaling voltages up, bridging networks, or isolating phases, carries specific mathematical properties, exact utility factors, and strict angular offsets. As power grids expand and merge, connecting new nodes always requires zero phase displacement. The angle of the voltage dictates the shape of the network. While we see a vast infrastructure of oil, copper, and steel, the modern power grid operates as a physical manifestation of geometric algebra.
In this session, Module CAT 017 covers advanced circuit design. Don't forget to like and subscribe to stay updated with our latest tutorials.